Hello, Joe here. Let's talk vectors. In this video, we're going to give an introduction to vectors. We're going to talk about the difference between a scalar and a vector. We're going to talk about some terms we need to know to understand vectors, and even some vector operations like vector addition and multiplication. So let's get started. So what is a vector? Well, let's first talk about what a scalar is. A scalar is just a quantity. It's a number. I could tell you I have 3 markers, and that's enough information to tell you how many markers I have. I don't need to give you any more information. However, some other quantities are not quite so simple. For example, let's say I have a little ant, and it's hanging out right here. And then I tell you the ant moved 3 inches. Where's the ant? Well, you don't really know, right? I could take my trusty ruler, and I could say, well, that ant could be 3 inches away here, or down here, or up here, and so forth. Basically anywhere on this circle is where that, it's not a good circle, I apologize. Anywhere on a circle with a 3-inch radius is where that ant could be. You need more information. You need a vector. A vector has 2 pieces of information: magnitude and direction. And I hope to show you in this video that they are equally important. At this point, you may be more familiar with the numbers and using the numbers. Well, the direction is just as powerful. So I could say this ant moved 3 inches straight up, and define that as an arrow where the magnitude is the length of that arrow, and it's 3 inches. The direction is straight up. We're going to use different coordinate systems to define direction. Let's look at some other examples of vectors. I just talked about displacement. This person's walking. You need a magnitude and direction to talk about that. Force is going to be a big one in statics. We're going to have force vectors, and they have both magnitude and direction. In this case, you see the force of gravity pulling the skydiver straight down. Velocity. Velocity also has a magnitude and direction. This race car, you could say it's going 100 miles per hour, but that's just the speed. Speed is the magnitude of velocity. To have velocity, you'd have to say it's going 100 miles per hour and give the direction. And of course, acceleration is also a vector. You're going to deal with velocity and acceleration more in dynamics. So we now know the difference between a scalar and a vector. Let's talk a little bit about some of the terms that we're going to use to describe vectors. You can see we have a vector v here, and this vector is defined by the arrow. There are different parts of this arrow. This end is called the tail. Oops. And the end with the arrowhead is called the tip. So this is the tip, and that is the tail. A line that connects the tip and the tail is called the line of action. And you can picture that line extending to infinity in both directions. The line of action is not the same thing as the white line of the arrow. The line of action is an infinitely long line that sets the direction of the vector. You notice the white line of the vector has a magnitude. In this case, it is looks like about 8 inches. So the magnitude of v would be 8 inches. Okay, the length of your arrow is the magnitude. The part without an arrowhead's the tail, the part with an arrowhead's the tip, and the line of action is setting the direction of that arrow. So those are all terms that you need to get familiar with. In addition to that, we need to know what sense means. The sense of a vector is the direction along the line of action of that vector. It is set by the arrowhead. V, in this case, is pointing in this direction. That's its sense. We could have V, we could have negative V, which would share a line of action with V, but it would have the opposite sense. It would have the arrowhead down here. This would now be the tip, and that would be the tail. Okay? So a sense is which way it's going on the line of action. The point of application of a vector is another term that can be important, especially for force vectors. The point of application is where that force is being applied on a body. For force vectors, this is really important because where the force is applied will affect the outcome, whether it's accelerating or moving or how it's feeling the forces. Other vectors, like moment vectors, they are called free vectors. A free vector is a vector that does not have a point of application. It can be moved and not change the effect. Okay, the other term is coordinate system. We're going to be defining several different coordinate systems. We're going to be talking about the Cartesian coordinate system. We're going to be talking about polar coordinates. One of the terms you need for polar coordinates is orientation. The orientation of a vector is really just an angle from a given reference line. I randomly chose this reference line. I meant for it to look horizontal. It doesn't really, that's okay. This is our reference line. This is a reference line, or sometimes called, this could be our reference, sometimes called a datum. And there's an angle from that. This is called our orientation. This one would be roughly 45 degrees. Looks more like 40 degrees. Okay, so that's called orientation. And finally, unit vectors. A unit vector is really quite simple. It's a vector whose magnitude is 1. I could make a unit vector that shares a line of action with my v vector. It would look like this. It would have a magnitude of 1 inch, and it shares both the sense and direction of my v vector. We are going to be using that a lot in this class. How do we separate out the two components of a vector? How do we separate out the magnitude from the direction? And how we're going to do it is with unit vectors. We'll get into that in more detail later. The next thing we need to talk about is notation. Perhaps you've used vector notation before. Hopefully you're very comfortable with it. If not, it's time to get comfortable with it. In the past, maybe you have labeled anything that could be a vector with a harpoon and called it vector notation. That's not exactly how we're going to do it, because sometimes we're going to use a reference to the same variable in both a scalar and a vector. We need to be able to tell the difference. What's the difference? Well, in some cases, we're just going to be referring to the magnitude. In other cases, we're going to be referring to it as a vector with a magnitude and direction. How do we distinguish the two? In printed material, we distinguish the two with bold. I honestly don't really like this because it's very hard for a beginning statics student to notice, right? Look at this V and look at that V. They look pretty much the same, but they're not. They're very different. This V has 2 pieces of information. It has the magnitude and direction. It is a vector. This one has 1 piece of information, just the magnitude. When you're reading your textbook, please be careful. Every time you see a variable that's in bold, make sure you tell yourself that's a vector. It is different from a scalar. Handwritten, it's a little bit easier to distinguish. For vectors, we use V with a little harpoon over it. It doesn't have to be V. We're going to be using A, B, C, whatever. You see a harpoon over it, it's a vector. And a scalar is just a V with no harpoon. So every time you write a variable without the harpoon over it, you're telling me it's a scalar. Make sure that's what you mean. Okay, maybe you've seen this before. With the absolute value signs around a vector. That means the magnitude of the vector. That is exactly the same thing as V with no harpoon. Okay? Why do we use this instead of this in statics? Well, because we're going to be writing a lot of scalars, and if we had to do this each time, it would be a lot of work. This and this are the same thing. Make sure that every time you see a variable with no harpoon that's not bold, this is what you think of. One more piece of notation is a unit vector. If it was a unit vector called V, we would put a little hat over it like this. And that hat means 2 things. It means I'm a vector and my magnitude is 1. Whenever you see that hat, you know that it's a unit vector. All right, let's get into some vector algebra operations. First, vector addition. I'm going to start off by defining 2 vectors. Vector A is going to be 3 inches. Vector B is going to be 4 inches. And they're going to be in the directions shown. This is A. This is B. Okay, now I want to find the sum of A plus B. A plus B equals R. R is going to stand for resultant. Oh, it's easy, right? 3 plus 4 equals 7, right? Wrong. I made a big mistake. And it's a mistake I see on so many papers when students are just starting out. This equation is written incorrectly. I'm adding the magnitude of A plus the magnitude of B and saying that equals the magnitude of R. Well, it doesn't. Why? Because we can't add vectors in the same way we add scalars. Vectors do not always share the same direction. If B happened to be in the same direction as A, that is the only instance that this would work, and the resultant vector would be 7. So how do I fix it? Well, it's pretty easy. The vector A plus the vector B equals the vector R. Although this looks very similar, this is a completely different equation. This is a vector addition equation. And how do we add vectors? Well, we use what's called tip-to-tail triangle construction, or the parallelogram law. And it turns out both of those are in essence the same thing. Let's do tip-to-tail construction. It's just like it sounds. We take the tip of one vector, we place it on the tail of another. So I'm going to take B, I'm going to move it over here and redraw it so that its tail lines up with the tip of A. It's still going to be 4 inches long. And then the resultant vector starts at the tail of A and goes to the tip of B, and that would be my R vector. This is called graphic addition of vectors. If you have two vectors that are drawn the correct magnitude in the correct direction, and you create a triangle, you can get out your protractor and measure, and you will find the magnitude. So you can actually do it graphically using a ruler, protractor, and you can find that relationship. Of course, there are other ways to solve it mathematically we'll go into in a little bit. But first, let's talk about the parallelogram law. This is triangle construction, but it's very similar to the parallelogram law. I chose to slide B to the tip of A. Well, what if I had instead taken A and put it on the tip of B? Well, that would look like this. This would be A of 3 inches, and you can see we get the exact same resultant vector. It doesn't matter whether we choose this side of the parallelogram or this side. If I draw these dotted lines, I think you can see that those add together to make a parallelogram. This is the parallelogram law. We have A on two sides and B on two sides, and the resultant vector is the diagonal of that parallelogram. Okay, it's very important that you can solve vectors by drawing pictures. Drawing pictures in statics is probably one of the biggest things you learn, is that mathematical analysis and problem solving really requires a good picture. Now, you don't have to be a good artist. It doesn't have to have, my lines are not always straight, but what they represent is important. You can solve the math by drawing the picture. So make sure you practice drawing the pictures and practice solving these. So how would we solve it? Well, once we have these drawn, we use our geometry. If this happened to be a right angle, it looks close, but not quite. If this happened to be a right angle, what would we use? Pythagorean theorem. 3 squared plus 4 squared is 5 squared, and R would end up being 5, not 7, like we saw at the beginning. If it's not a right angle, we're going to have to do the cosine or sine law. Here's just a reminder. The law of sines, if we have capital A, B, and C as the length of the sides, we have lowercase a, b, and c being the angles. Note how lowercase a is directly across from capital A, and lowercase b is across from B, and so forth. The law of sine says sine of A over A equals sine of B over B equals sine of C over C. So if we have one side and one angle, if we have one angle and two sides, we can find the other angle. If we have two angles and one side, we can find the other side. So we draw the picture. We write all of our knowns. In this case, we have 3 and 4. That's two sides. If we also had an angle, let's just say this is not quite 90. It looks a little bit more 94 degrees. And we wanted to know what R was. Let's try the cosine law. the law of cosines says that if we have two sides in an angle, we can solve for another side. Hey, that's exactly the situation we have. 3 inches, 4 inches, that's two sides. We have one angle. We want to solve for r. Okay, so we want to use the equation that will solve for r. It doesn't really matter which one of these you choose down here. They're really all the same thing. Note that there's only one angle in the equation. We want that angle to be the one across from the one we want to solve. R squared is equal to a squared plus b squared, 3 squared plus 4 squared, minus 2 times 3 times 4 times the cosine of the angle across from r, which is 94 degrees. We can solve that equation, and we're going to get our magnitude of r. So once you solve this cosine law, you have r that goes in here, and you could solve for the angle A or angle B or both, depending on what the question asks. So hopefully that's a quick example of how you can use graphic vector addition and the cosine and sine law to solve for the resultant vector r. Okay, so that was vector addition. Now let's look at some other vector algebra operations. The first one we're going to look at is multiplying a scalar by a vector. This one's pretty easy. We have vector v here. If we want to multiply it by a scalar, let's say 2. 2 is a scalar. It's only going to affect its magnitude, not its direction. So it's going to double its magnitude. So v, 2v, is twice the length. If we decide to multiply it by a negative number, it keeps the same direction but changes the sense. Notice how the arrowhead is on the opposite side. We still have that same line of action that goes to infinity in both directions, but the sense has changed. And you can do both at the same time. You can multiply it by negative 3, which would triple its length but change the sense. How about subtraction? Well, we just learned two operations. We learned vector addition, and we learned multiplication by scalar. Vector subtraction is just the combination of those two. Subtraction equals scalar multiplication plus addition. If we have these two vectors, vector A and vector B, and we want to subtract them, A minus B is going to be A plus negative 1 times B. Okay? So I take B, multiply it by negative 1. Notice the sense changed. Now I'm going to use vector addition. Watch B. I'm going to slide it tip to tail with A. So I now have A plus negative 1 times B. And of course, R is going to be the resultant of those two. You might be asking yourself, what if I need to add more than 2 vectors? You can just continually do the vector addition. So if we have A plus B plus C, we're going to first multiply, we're going to first add A and B by sliding B down, do our tip to tail triangle construction. You can see we get a resultant vector here, which is A plus B. We are then going to add C to that, and we get A plus B plus C. Note that we don't have to do the resultant step. We can just do tip to tail, A to B, and then tip to tail, B to C. If I take out that intermediate step, we still get the same answer. This is graphic representation of vector addition. Make sure you're drawing the pictures. It's very important to solve problems. And let me show you an example of why. All right, let's try an example problem. Went out to my garage and I found a metal bar hanging from a chain. So we've got this metal bar hanging from the chain. And if you notice, the two lengths of chain are not the same length. You have a shorter one and a longer one. The question is, which one has more force in it? Which one is holding more force? Are they the same? Is the shorter one greater, or is the longer one greater? Now, notice that there are no numbers in this problem. I'm just asking you which is greater. Go ahead and hit pause and think about it for a minute. Maybe draw some pictures and see if you can figure out a plan of action for this problem. Okay, your first response might be, we don't have enough information. And that's not true. We can solve this problem. The way that you start every problem is going to be the same. You write down what you know. And this is how we do it. We're going to actually write the word given and then write down what we know. A lot of times this will have numbers in it, but not always. So think about, what do we know about this problem? We don't know any numbers, but vectors have two components, magnitude and direction. Do we know any directions? Well, here's a rope. If we were in person, I'd throw this to a student and you'd hold on to one side. I'm going to do both sides this time. So if I hold on to one side of the rope with one hand and the other side of the rope with the other, which way can I move my hand? Can I move it away from me? No. Right? I push on the rope, it gives way. I can't move my left hand without pulling. Okay? In what directions can I pull? Can I move it this way? Can I move it towards the screen and back? No. I only have one choice. I can pull the hand towards me. Why? Because ropes, chains, they only pull. That's the only thing they can do. What does this tell us? It tells us that the force in a rope or a chain is in the direction of the rope and chain. Now this may seem obvious, but it's something that we need to use mathematically, and it's something that is easy to overlook. So what's our given? Force, or tension in this case, the tension in the chain is along the chain. Okay, what else do we know? Well, if I go back to the problem, do we know the direction of the force on top? The force in this chain? Well, I just told you it's got to be along the chain. Would you expect that chain to be vertical? Well, of course, right? It's acting against the weight of the bar, and the bar pulls straight down because of gravity. So yes, this chain is vertical. What does this chain share with our vector addition? Well, we know the resultant has to be in the same direction. Otherwise, this could not be balanced. It could not be in static equilibrium. Now, we will talk more about free body diagrams and how to draw those in chapter 3. But in this case, we're going to start just by drawing a diagram of the forces acting on this point right here. The first step to a free body diagram is always choose your body. My body is going to be this junction right here. Okay, so what do I need to do? I'm going to hold this up near my screen, hopefully without breaking it. And I'm going to draw my body. My body is this junction right here, and it looks like a little dot. Okay, and then I'm going to draw the direction of the tension along the rope. By the way, this is really heavy. And this is going to be along that rope. Now, I don't know their lengths, but I do know their directions. They have to be along the chain. So I drew them along the chain. I'm going to go ahead and make them the same length because I don't know any better. And then we'll adjust them if needed. So this one I made 6.5 inches. I'm going to make this one also 6.5 inches. And there we go. Okay, now I need to do my tip to tail triangle construction. Okay, so I'm going to take this vector and I'm going to slide the tail down to the tip of this vector. And you notice I'm also making a parallelogram. Okay, now I'm going to draw the resultant vector. Well, wait a minute. If tension is along the chain, I know that has to be in this direction. That has to be in that direction. Which direction does my resultant vector have to be in? Well, it has to be vertical. This chain is vertical. Therefore, my resultant vector has to be vertical. So I'm going to draw it straight down. And where it crosses has to be the tip of this vector. What does that tell us? Well, it tells us that I have to shorten this vector. We're going to call this side A and this side B. A is the shorter chain. B is the longer chain. Side A, I had to shorten in order to have this be vertical. There's no other way for it to be vertical, which means there is more tension in chain B because it has a longer magnitude in order to make this triangle. Note, I didn't have to use any values, right? If I did determine how much weight that weighs, if I put it on a scale, I could come up with the magnitude of this resultant force and put that on here, and then that would allow me to find the magnitudes of these two if I knew at least one angle. But you can see just this distance here, A has to be shorter than B in order for that to be vertical. Hopefully that gives you an idea of how powerful both components of a vector are. I solved an entire problem without using any numbers. So we don't just need magnitudes. Sometimes we can just use directions. Hopefully that was helpful. I look forward to working with you. Let me know if you have any questions.